Okay, we're going to keep going here on Chapter 7, the central limit theorem. This one is a little bit tricky. It's important you get conceptually, and I really want to focus on this because I remember when I was taking statistics, I really misunderstood this concept, and it made the class infinitely more difficult. So this is really important that we understand, and there's a key piece that I really am going to emphasize. So right now, this is a little bit of word vomit here. It's kind of easy to get lost in, but I'll go through it really quickly. So the central limit theorem for sample means, so it's not always for sample means, but this is an example they're giving, says that if you keep drawing larger and larger samples, such as rolling 1, 2, 3, 4, 5, finally 10 dice, and calculating their means, the sample means form their own normal distribution. That's the key of the central limit theorem. To put it more formally, if you draw random sample sizes of size n, the distribution of the random variable x, which consists of sample means, is called the sampling distribution of the mean. The sampling distribution will be normally distributed. So what this really means in practice is something like this. And this kind of will demonstrate the power of the central limit theorem. So if we have a population distribution, and we know it is bimodal shaped, it's not normally distributed. But this is a single sample. Now, instead of taking an observation, so a sample is made up of individual observations. Now, instead of looking at a single observation, we're going to look at a single sample and the mean of the single sample. That's why we have the mean here. Now, if we add all those samples together, we end up with this. So think of these as observations and these as samples. It's completely different. Like I said, that is kind of confusing. There is another video I'm posting to Khan Academy where he breaks this down a little bit, step by step, and I think it's a great video, and it's, like I said, it's really, really important that we understand this concept. Now, this also will apply to more than just the mean. So here we have the mean, but this would also apply to the standard deviations and just other characteristics about samples. So the key piece here is this is almost a law of nature. It's known to be true. And that helps us so much when we start to think about inferential statistics, because we really see this normal distribution, this normal shape, and that's where we use z-scores, t-scores, and so on and so forth. But we know that we can use them because this is a very natural shape. This is what occurs the more samples that we take and compare. A little more here. The central limit theorem is really a recognition that we're drawing, or that any sample we draw is really only one from a distribution of samples. Okay, so now that thing that we just created is a sampling distribution, not a population distribution. And that is the source of the central limit theorem, really. This is my takeaway. So this isn't, necessarily what you should stick by as a top 4, but this is why I think the sampling distribution is so important. One, it follows a rule of the world, the central limit theorem. This is just observed time and time again, almost like the Pythagorean theorem. We just kind of know it to be true, which makes it very natural and a great basis for the field. Number 2, it applies to multiple characteristics, so it's not just about the mean. It can be about the standard deviation and other characteristics. And 3, it can keep us from saying, well, I think I could have drawn an outcome once, anything can happen once. Instead, we have to say this group of individuals or this group of outcomes could have an outcome that happens once. So this grouping, maybe I mistyped this here, but a sample could have an outcome. So what the sample itself is saying has to have an outcome that happens once. So you have to gather up enough information that it's not one person in one place doing one thing. It's a group of people in one place doing one thing. And that is really the final piece we need to get into inferential statistics. I think since we are looking at samples, it becomes rarer and rarer to have outliers. Thus, we can see that outliers are contradictory to what we know. If we draw samples that are really far apart from what we expect, maybe we should be expecting something different. So, what that tells us is if we are drawing a sample, this is not an individual observation, but a sample. So I pull 20 people, not one person, 20 people, and they all tell me that, I'm not going to worry about it, but they have a value down here, and this is the mean. Well, this is such a far outlier, and this isn't one person. This is an entire sample of people. Well, maybe this wasn't correct, right? Maybe I was wrong about the original population. That concept right there is inferential statistics. That's everything that we're going to be doing from now on. When is the population true? When is it false? Based on the samples that we have and new samples that we get, can we say that this is correct or incorrect?